What would happen if we were suddenly able to harness the power of the sun? For more than 7 decades, the journey to control fusion energy has been one of humanity's biggest challenges. Scientists have designed machines in an attempt to recreate the conditions for fusion on Earth. If successful, the implications would be transformative. Everything in our world, the price of goods, the cost of manufacturing, where people can live, how far we can travel, is ultimately determined by the cost of energy. Fusion would not only provide clean power, but would also remove energy as a limiting factor, potentially triggering an economic transformation comparable to the Industrial Revolution. But controlled nuclear fusion has famously been a kind of scientific joke, a future that has been, and always might be, 20 years away. However, that narrative may be changing. In 2022, scientists at the National Ignition Facility in California announced that they had achieved the impossible. For the first time, a fusion reaction produced more energy than it took to start the reaction. That breakthrough, called ignition, sparked a renewed excitement in fusion, and a renewed optimism that energy-abundant future may be closer than we thought. The possibility of powering our world with clean and abundant energy has led to billions of dollars invested in the past few years. Sam Altman has invested hundreds of millions into Helion, Jeff Bezos is backing General Fusion, Bill Gates is backing Commonwealth Fusion Systems. And the ever-growing number of fusion startups are making bold claims. Fusion power, connected to the grid by 2030. But is that realistic in terms of the real state of fusion energy today? And if it is, what would that mean? What would we do with that kind of power? How would that shape our planet, our future? And what happens when a technology born from the hydrogen bomb is finally in the hands of everyone? The quest for a star on Earth, the world that H.G. Wells envisioned where that perpetual struggle to live on the bare surplus of nature's energies will cease to be the lot of man, was not born in a university lab or a startup. It was born in the total secrecy, in the paranoia of the Cold War. In the early 1950s, the United States Atomic Energy Commission quietly began a new program. Its codename, Project Sherwood. The goal of this project was to achieve controlled thermonuclear fusion. But this was not purely for utopian energy. The driving force, as with a lot of physics research at the time, was military. The calculations showed that a fusion reactor could, in theory, be a factory for high-energy neutrons, a machine to breed plutonium for an endless arsenal of hydrogen bombs. For nearly a decade, the work was hidden. At Princeton, Lyman Spitzer was developing his Stellarator. At Los Alamos, James Tuck, whose work helped inspire the program's name, was building his Perhapsatron. They were all racing, blind, to build a star in a bottle, with no idea if they were in first or last place. But the Americans were not the only ones working in secret. Across the Iron Curtain, Soviet physicists were also on the hunt. They, however, were on a different and ultimately far more fruitful path. At the Kurchatov Institute in Moscow, 2 of the nation's most brilliant minds, Andrei Sakharov and Igor Tamm, both who would later win the Nobel Peace Prize for their human rights activism, had conceived of a new design in 1951. They theorized that a donut-shaped ring, or torus, wrapped in powerful magnetic coils could create a stable bottle for the plasma. They called it a tokamak, a Russian acronym for toroidal chamber with magnetic coils. The West knew nothing about it. That is, until 1956. In an act of almost unbelievable audacity, the Soviet leader, Nikita Khrushchev, visited the United Kingdom for a state trip, and he brought with him Igor Kurchatov, the father of the Soviet atomic bomb. Kurchatov, with the Kremlin's permission, traveled to the Atomic Energy Research Establishment in Harwell, in the heart of Britain's nuclear research program, and delivered a lecture. In that lecture, he revealed the entire Soviet fusion program. He described their tokamaks, their massive pulsed power machines, and he shared data showing that they had achieved plasma temperatures and confinement times far beyond anything the West had even theorized, let alone accomplished. The British scientists in the audience were stunned. Some reports say they were laughing at the start, thinking it was absurd propaganda, but then were in a deathly state of silence at the end. Kurchatov's 1956 lecture lit a fire under the West. It proved that secrecy was not only pointless, but a disadvantage, as it became clear that scientists across the globe were all struggling with the same physics. Kurchatov's lecture led directly to the 1958 Atoms for Peace conference in Geneva, where a full declassification, now including the US, UK, and Soviets, finally took place. It was there the Americans revealed their stellarators, and the full, detailed schematics of the Soviet tokamak were laid bare for all to see. And the surprise from 1956 was confirmed. They were all, independently, stuck on the exact same, seemingly impossible problems. The dream of a secret weapon had failed, and in its place, a 70-year international journey to control fusion had begun. The fundamental challenge they all ran into is the same one that still defines this entire story: the concept of net energy positive. It turns out that making fusion happen is, on a certain level, easy. Thousands of amateur physicists and high school students have built small working fusion reactors in their garages. These are called fusers, and you can see the tiny glowing star of plasma inside. But here's the critical distinction. That garage reactor, and every single experiment for the next 7 decades, was power negative, meaning it took far more electrical energy to run the magnets, the vacuum pumps, and the heating systems than anyone got out of the tiny fusion reaction itself. That has always been the major barrier. The goal is not just to make fusion, it's to get more power out than you put in. This net positive barrier has been the wall for 70 years. But what if I told you that just a few years ago, for the first time in human history, someone finally breached it? On December 5th, 2022, at the Lawrence Livermore National Lab in California, an experiment was conducted that would fundamentally alter the fusion narrative. The facility is the National Ignition Facility, or NIF. It's a massive structure occupying the space of 3 football stadiums. Inside, 192 of the world's most powerful lasers are aimed, with microscopic precision, at a single target: a peppercorn-sized capsule containing a fuel of hydrogen isotopes, deuterium and tritium. At 1:03 a.m., the lasers turned on. They delivered 2.05 megajoules of energy to that tiny target. A fraction of a second later, the resulting fusion reaction produced 3.15 megajoules. For the first time in history, a controlled fusion reaction had achieved a Q value greater than 1. The reaction had produced more energy than the energy delivered to it. This was ignition. The 70-year barrier had finally been overcome. The public announcement a week later was a global media sensation. The US Secretary of Energy declared it one of the most impressive scientific feats of the 21st century. The headlines were euphoric. We had solved fusion. We had harnessed the power of the sun. But in the days that followed, a more sober, complex, and investigative picture began to emerge. The problem was in the definition of net energy. That 3.15 megajoule output was more than the 2.05 megajoules of laser light that hit the target. But to create that 2.05 megajoule pulse, NIF's 192 lasers had to pull over 300 megajoules of energy from the electrical grid. So, to be clear, this was not net positive in any practical electrical sense. The experiment consumed, from the wall plug, over 100 times more power than the fusion reaction itself produced. Now, NIF was never designed to be a power plant. It's a research facility funded primarily by the National Nuclear Security Administration to study the physics of thermonuclear reactions in order to maintain the US nuclear weapons stockpile. But that critical scientific nuance ended up buried in the sensational headlines that followed the announcement. And the excitement from the success of the experiment opened up a wave of investor capital. It gave a new, powerful, and some would say misleading, talking point to the dozens of private fusion startups that had been, until then, working in relative obscurity. Suddenly, the claims, once cautious, became stronger and bolder. The narrative was no longer, maybe in 30 years. Now it was, we will see fusion power connected to the grid by 2030. We are, without question, scientifically closer than we've ever been to having controlled, energy-positive fusion. But yet, the public is being sold a timeline that still seems impossibly optimistic. So, what's the real timeline for fusion? And between the multinational, publicly funded collaborations and the growing number of emerging private startups, who's really going to get us there? Before we keep going, if you want more deep dives into the exciting questions in science, don't forget to subscribe. And if you're enjoying this video, give it a like. I really appreciate your support. The NIF breakthrough and the subsequent media coverage served to bifurcate the global path to fusion. The long-standing state-funded public sector research was suddenly and aggressively challenged by a new, fast-moving, and well-funded private sector race. The traditional approach is embodied by ITER, ITER, the International Thermonuclear Experimental Reactor, located in the south of France. It is arguably the most complex engineering project in human history. It's a vast scientific collaboration involving 35 nations and designed to be the definitive open access proof that a tokamak, the toroidal magnetic confinement device, can sustain a burning plasma and produce a net energy gain defined as a Q value of 10. This project is defined by its immense scale and methodical multilateral pace. But ITER has been plagued by major setbacks, from manufacturing defects in critical components to complex international supply chain failures. These have led to a cascade of delays and a budget that has escalated to over $20 billion. But since the 1980s, there have been a growing number of private fusion companies, and this number really exploded after the ignition breakthrough in 2022. These private companies are defined by venture capital, proprietary technology, a new class of investors, and bold technological bets. On one side, you have Commonwealth Fusion Systems, or CFS, an MIT spin-off backed by investors including Jeff Bezos and Bill Gates. CFS is not attempting to reinvent the tokamak. They're betting that they can perfect it. Their primary innovation is not a new reactor design, but a new magnet. For decades, tokamaks have been built with low-temperature superconductors, which must be cooled with liquid helium to 4 Kelvin, just a few degrees above absolute zero. This is an enormously complex and expensive cryogenic process. CFS, in collaboration with MIT, has developed revolutionary new magnets from high-temperature superconducting tape called REBCO, rare earth barium copper oxide. These magnets can produce immensely more powerful magnetic fields. A stronger field permits a much stronger confinement of the plasma, which in turn allows the entire device to be dramatically smaller. Their test reactor, SPARC, is projected to be approximately 1/40th of the volume of ITER, yet is designed to achieve similar performance metrics. This is the smaller, cheaper, faster bet, a bet on perfecting the tokamak. On the other side, you have companies like Helion Energy, backed with hundreds of millions from Sam Altman. Helion's bet is far more radical. They're not building a steady-state tokamak at all. Helion's machine is a linear, cylindrical device that operates in a pulsed fashion. It works by forming 2 separate toroidal plasma structures, or plasmoids, at either end, and then accelerating them into a central chamber at over 1 million miles per hour. They collide and are magnetically compressed, initiating a fusion reaction. The most exciting claim in their model, however, is direct energy conversion. A tokamak is, at its core, a 21st century furnace, designed to create heat to boil water and spin a steam turbine. Helion claims that as their fused plasma expands, it will push back against that magnetic field, directly inducing an electrical current in the machine's coils. In theory, this would bypass the entire inefficient steam cycle. But the reactor designs are not the only considerations when building fusion technology. Private companies are also applying new technology to fusion: AI. A tokamak plasma is a chaotic 150 million degree phase of matter, constantly on the verge of collapse from instabilities. Since the start of fusion research, scientists have tried to control the shape of this plasma with pre-programmed models. But in 2022, a landmark paper was published. Google's DeepMind AI division had taken control of a research tokamak in Switzerland. They trained a deep reinforcement learning algorithm and gave it full, real-time authority over the magnetic coils. The AI learned to predict and prevent plasma instabilities before they could form. It learned to sculpt the plasma into novel, highly efficient configurations, some of which human physicists had never even theorized. This is the thesis of the next generation of fusion technology. Artificial intelligence is the new tool that may finally solve the plasma physics problems that have plagued fusion scientists for years. This high-stakes race between public projects and private companies is not only a two-way competition. There's a third player, and they may already be winning. While ITER struggles with delays and Western startups race for venture capital, China has pursued a unified, top-down national strategy. Fusion is explicitly designated as a strategic frontier in China's 14th five-year plan. At the Institute of Plasma Physics, China's flagship tokamak, the Experimental Advanced Superconducting Tokamak, called EAST, has been steadily breaking world records. Called China's artificial sun, it is one of the very few fully superconducting tokamaks in the world, and it's been used as a testbed to push the absolute limits of fusion science. In January 2025, the EAST reactor achieved a new milestone. It successfully generated and maintained a steady-state high-confinement plasma for 1,066 seconds, breaking its own previous record of 403 seconds. To put this in perspective, that's 17 minutes of sustained, controlled, 180 million degree plasma. It's a huge engineering and scientific achievement, demonstrating a mastery of plasma stability that is years ahead of many competitors. But EAST is merely a testbed. China's real objective is a machine called the CFETR, the China Fusion Engineering Test Reactor. While ITER is a scientific experiment designed to prove a Q value of 10, the CFETR is being designed from the ground up as a demonstration power plant. It's planned in two phases. Phase 1, to demonstrate steady-state operation and, critically, tritium self-sufficiency, and Phase 2, a 1 gigawatt class reactor designed for grid connection. To solve the key engineering problems for this machine, the same problems plaguing everyone else, China has built another new facility, the Comprehensive Research Facility for Fusion Technology, or CRAFT. In October 2025, they announced a major milestone, the successful development and testing of the world's largest diverter prototype, a component essential for handling the reactor's intense heat exhaust. This is what a unified national strategy looks like. Test reactors, engineering facilities, and state-backed private companies all advancing in parallel. The US led on nuclear fusion for decades, but with recent advances, China is in position to take the lead. And that's creating a new geopolitical reality, the fear that the US will lose this 21st century energy race to China. At the same time, Japan's JT60SA tokamak, a joint EU-Japan collaboration, achieved first plasma in 2023, and is now the world's largest operating tokamak, running experiments while ITER remains under construction. And South Korea's K-Star reactor has also set records for high-temperature plasma confinement and is advancing its own superconducting tokamak technology. So we have a global race, the slow, methodical public science of ITER, the fast, disruptive startups of Silicon Valley, and the record-breaking national programs of China. But all three face the same unsolved engineering problems, unless there is an alternative path entirely. This three-way race seems to be a battle over one single design, the tokamak. But what if the tokamak itself, the machine that Andrei Sakharov envisioned in 1951, is a flawed concept? This brings us to the dark horse of fusion, a machine that was actually invented first. In 1951, the same year Sakharov was theorizing the tokamak, an American astrophysicist at Princeton invented a device he called the stellarator. Under the codename Project Matterhorn, it was the original focus of America's Project Sherwood. The stellarator and the tokamak are both toroidal, or donut-shaped machines, but they solve the problem of confinement in fundamentally different ways. A tokamak is geometrically simple. To create the twisting magnetic field needed to hold the plasma, it must induce a massive electrical current inside the plasma itself. This plasma current is the tokamak's greatest strength. It's a simple way to heat the plasma. But it's also a weakness. It's inherently unstable, prone to disruptions that can extinguish the reaction in milliseconds and damage the machine. This is why tokamaks generally must run in pulses, not continuously. A stellarator is the opposite. It's an engineering nightmare to build. Its magnetic coils are not simple rings. They're complex, twisted, non-planar shapes. But the purpose of this complexity is to create the entire magnetic bottle using only the external coils. It does not need a massive unstable current within the plasma. So the result? The plasma inside a stellarator is inherently stable. It's not constantly on the verge of collapse. And most importantly, a stellarator can run in steady state, meaning continuously. And this would be a non-negotiable advantage for a commercial power plant. For a long time, the design of a stellarator was seen as too complex to build. But new supercomputers and advanced manufacturing have changed that. In Germany, the Max Planck Institute has built the Wendelstein 7X, a $1 billion stellarator designed to prove this concept. And it's working. Wendelstein 7X has set one world record after another for high-performance, long-duration plasma, proving the intrinsic stability of the stellarator design. While the world bets on the tokamak, this dark horse is quietly proving that it may be the more stable and ultimately more viable path to a power plant. But whether the most successful design will be a tokamak or a stellarator or a pulse device, all of them must solve the same fundamental physics problem: achieving and maintaining the conditions for fusion. The challenge is this. In DT fusion, you must heat hydrogen isotopes to temperatures exceeding 100 million degrees Celsius, 7 times hotter than the core of the sun. Then, you have to confine this plasma long enough for fusion to occur, and then extract more energy than you put in. This is where reactor design, as well as fuel choice, come into play. Not all fusion reactions are created equal. The reason most major projects focus on deuterium-tritium fuel is that it's the easiest path, requiring the lowest ignition temperature at around 100 million degrees Celsius. And with this reaction, the probability of fusion actually occurring is high. But DT fusion comes with severe drawbacks. It produces high-energy neutrons that damage the reactor materials. And, while deuterium is abundantly found in seawater, the reaction also requires tritium, which is rare on Earth. Alternative fuel options sound appealing, but are difficult in their own way. Deuterium-deuterium fusion still produces fewer neutrons than DT fusion. The problem with that reaction is that it requires temperatures approaching 500 million degrees, 5 times hotter than DT fusion. Then there's the holy grail, aneutronic fusion reactions like hydrogen-boron or deuterium-helium-3. These produce no neutrons, meaning no neutron damage to the reactor, no radioactive waste from activation, and no tritium requirement. These would mean clean fusion from abundant reaction materials. But they require temperatures in the billions of degrees. At those temperatures, the energy loss from radiation becomes almost too large. The plasma radiates away energy faster than fusion can replace it. This is why, despite decades of research, no one has achieved net energy from aneutronic fusion yet. So the global fusion research projects like ITER made a choice. Master DT fusion first, despite its problems, because it's achievable with current technology. Then, after that's achieved, perhaps decades later, use those operating reactors as testbeds to develop the more difficult fuel cycles. This is the gamble. Solve the easier physics problem with DT fuel first, even though it creates its own challenges in terms of engineering problems. So let's look into some of those problems that arise from DT fuel fusion reaction. Assume for a moment that the physics problem is solved. A company, ITER or China, successfully builds a reactor that reliably produces net positive energy using deuterium-tritium fuel. This is the moment every press conference has promised. This is also the moment when the real problems begin. The first and most important reality is this: fusion energy will not be free. In fact, at first, it will likely be one of the most complex and expensive forms of energy ever created. The reason for this lies at the heart of the DT reaction. When deuterium and tritium fuse, they create two things: a single high-energy helium atom and a single very high-energy neutron. The helium stays confined by the magnets, providing the heat that will be used for energy. The neutron, however, has no electrical charge. It's not affected by the magnetic fields, and it will fly out of the plasma at roughly 17% the speed of light. It flies out and slams into the inner walls of the reactor. This constant high-energy bombardment causes a phenomenon known as neutron embrittlement. The neutrons damage the atomic structure of the steel encasing the reactor, making it brittle, weak, and over time, unusable. Furthermore, This bombardment activates the steel, turning the entire reactor vessel into intermediate-level radioactive waste. This is called the neutron problem. It's a twofold crisis. It destroys the reactor from the inside out, and it creates a massive waste stream. So, how do you solve it? This is where the engineering gets truly science fictional. The solution is to not have a solid wall in the first place. The leading design is called a liquid metal breeding blanket. The idea is to build a reactor vessel with inner channels and then continuously flow a liquid metal or molten salt through those channels. The leading candidate is a mixture of fluoride lithium and beryllium. This flowing liquid blanket is designed to do 3 critical jobs at the exact same time. First, the liquid absorbs the high-energy neutrons before they can slam into the structural steel. This shields the reactor, dramatically extending its lifespan. Second, the liquid contains lithium, which, when struck by a neutron, reacts to form a new tritium atom, the reactor's fuel. And third, the liquid, by absorbing all that neutron energy, becomes extremely hot. This superheated liquid is then pumped out of the reactor into a heat exchanger where it boils water and drives a steam turbine. This liquid blanket is the theoretical solution to everything. It's the shield, the fuel breeder, and the energy transfer mechanism, all wrapped in one. It's also a technology so complex that it has never been tested at a commercial scale. So, reactor designs currently under construction are dependent on this technology in many ways, especially for that second job, breeding the fuel. This brings us back to the most urgent challenge for the entire DT fusion economy, the Tritium Crisis. Tritium is a radioactive isotope of hydrogen with a 12-year half-life. It decays, and it's so rare that the entire global non-military stockpile is estimated to be, at most, 20 to 25 kilograms. To put that in perspective, a single 1 gigawatt fusion power plant is projected to consume 55 kilograms of tritium per year. ITER alone is expected to consume more than half the current global inventory over its operational lifetime. So, since there are less than 10 kilograms of naturally occurring tritium on Earth, where does the rest of our current supply come from? The answer is that it's almost entirely a byproduct of a specific type of Canadian heavy water fission reactors known as CANDU reactors. These reactors, originally built in the 1970s, produce about 2 kilograms of tritium per year. But that supply chain is limited, and most of that tritium produced is already earmarked for ITER's research. Projections show that by 2055, after ITER completes its run, only 5 to 14 kilograms of commercially available tritium may remain, potentially insufficient to start even a single demo reactor. So this means that the tritium breeding blanket technology is a requirement for any company planning to use DT fuel, which is about 70% of the field. Any DT fusion power plant must be a tritium-positive machine. It must breed more tritium than it consumes to keep up with the fuel consumption if we're going to keep improving fusion technologies and meet our energy demands. So, the engineering challenges become clear. A machine of immense complexity with a reactor wall that becomes radioactive waste after decades of operation. This wall must be shielded by a flowing liquid metal blanket, which has never been demonstrated at scale, that simultaneously must breed the reactor's own fuel through neutron interactions with lithium. If the blanket fails at either function, shielding or breeding, the entire system fails. This is the machine that must now compete, on cost, with the simplest energy source we have, the sun. Wind and solar energy are already competitive in terms of cost with power from gas and coal, even without subsidies. So how would a technically complex, multi-trillion-dollar fusion reactor, with its huge unsolved maintenance and fuel breeding problems, actually compete on the grid? That's a major question we have to ask. If fusion might be more expensive than solar and has these massive unsolved engineering problems, why are we even bothering? What can fusion do that solar and wind or our current energy supplies can't? That's the big question. And that's what we need to consider when thinking about a future that could run on fusion power. More than the technical challenges, the cost, or even the delays in projected timelines, fusion power could change the way we think about energy and what we can do with it. Solar and wind are amazing in many ways, but they're intermittent. They produce power only when the sun shines or the wind blows. They can't, by themselves, provide the base load energy that our 21st century civilization demands. That minimum, constant, 24/7 power is something that, as of now, nuclear fission, coal, and gas provide. Fusion would be a new and constant supply of clean energy. And, once successful, nuclear fusion would unlock applications that are currently, from an energy standpoint, completely impossible. The first, and most obvious, is water. We're a planet that's 70% water, yet we're facing a global crisis of freshwater scarcity. The solution is desalination, but it's a famously energy-intensive process. Providing clean drinking water for all 8 billion people is feasible with current technology, but requires massive investments in infrastructure, policy change, and sanitation facilities. To also provide water for a new agricultural revolution and to address some other UN Sustainable Development Goals would require a great amount of energy. Fusion is the only source that could, in theory, power the necessary desalination plants to meet these goals without interruption and without emissions. But that's just the beginning. The second application is the climate. Currently, some form of carbon dioxide removal is seen by many scientists as essential to limiting dangerous climate change. And one way to achieve this is through direct air carbon capture. This technology is currently possible, but it's also very energy intensive. To capture a single ton of carbon dioxide from the atmosphere with current technology requires between 2,000 and 3,000 kilowatt hours of energy. To capture our annual global emissions would require, by some estimates, doubling the world's entire current energy supply. A huge portion of that energy is not even electricity. It's high temperature heat, a co-product a fusion plant could provide in abundance. This is the kind of global scale engineering that fusion unlocks. And this kind of energy source would likely power a new industrial ecosystem. But the real game changer, the application that would truly allow us to advance in a new way, is space. We're currently limited to chemical rockets for space travel. A fusion rocket, or direct fusion drive, would enable sustained, high-speed propulsion over long distances. Instead of brief acceleration burns followed by coasting, a fusion rocket could provide continuous thrust, dramatically reducing travel times to Mars and the outer solar system. And this is where the fuel story gets really interesting. The DT reaction, the one that causes all those neutron and tritium problems, is not the only way. Remember aneutronic fusion, like the reaction between helium-3 and deuterium. This is clean, it's safe, and it's the perfect fuel for a rocket. The only problem is that helium-3 is almost non-existent on Earth. It is, however, abundant on the Moon. For billions of years, the solar wind has bombarded the lunar surface, embedding this rare isotope into the regolith. Private companies, like the startup Interloon, and even state-backed players are already drawing up plans to map and mine the Moon for helium-3. Interloon has raised millions and secured agreements, including a contract with the US Department of Energy to deliver 3 liters of lunar helium-3 by April 2029. They've also secured a NASA partnership and a partnership with quantum computing firm Maybell Quantum Industries. Their plan is this. First, a prospecting mission in 2027 to measure helium-3 concentrations at a target site near the lunar equator, followed by a 2029 pilot plant featuring robotic excavators designed to process 100 metric tons of moon soil per hour. But Interloon's primary near-term market isn't fusion at all. It's quantum computing. Helium-3 is essential for the dilution refrigerators that cool superconducting quantum computers to temperatures near absolute zero. At current prices of roughly 20 million per kilogram, the quantum computing market alone could justify lunar mining operations decades before helium-3 fusion even becomes viable. There are also secondary applications as well. Advanced medical imaging systems and neutron detection for homeland security. What Interloon represents is the emergence of an extraterrestrial supply chain, proving that space resources can be commercially harvested, processed, and sold on Earth. State-backed programs have explicitly identified lunar helium-3 as a strategic resource, framing it as a national security issue. The race to the moon is now about controlling the fuel supply for technologies that don't even exist on Earth yet. And the future of fusion may be linked to this supply chain. So this brings us to the next question. What about the dangers of fusion? The first and most prominent fear is the one we associate with nuclear fission, a meltdown. When people hear nuclear energy, they think of Fukushima or Chernobyl. That fear, along with cost, is a primary limitation of nuclear fission implementation. But this is another area where fusion differs. A Fukushima-type nuclear accident is not possible in a fusion reactor. The ITER organization itself states that fusion energy production is not based on a chain reaction, as fission is. Plasma must be kept at very high temperatures with the support of external heating systems and confined by an external magnetic field. Every shift or change of the working configuration in the reactor causes the cooling of the plasma or the loss of its containment. In such a case, the reactor would automatically come to a halt within a few seconds. For this reason, fusion reactors are considered to be inherently safe. Fusion is still a nuclear technology though, thus there is a danger from radioactive waste. The DT reaction, as we've established, unleashes a stream of high-energy neutrons. That neutron embrittlement that damages the reactor also activates the material. The neutrons bombard the steel walls of the reactor, and the atoms in that steel become radioactive. To be clear, this is not high-level, long-lived waste like the spent fuel rods from a fission plant, but it is a massive volume of intermediate-level radioactive waste. The entire 10,000-ton reactor vessel, after a few decades of operation, would be radioactive and must be decommissioned, dismantled, and buried as nuclear waste for, by some estimates, 100 to 300 years. And then there's the most concerning danger: weaponization. Fusion is the science of the hydrogen bomb. Project Sherwood was born from a desire to make plutonium for those bombs. A DT fusion reactor is, by its very nature, a tritium breeding facility. Tritium is the single most critical, regulated, and essential ingredient for a modern thermonuclear weapon. A world with a global fusion economy is a world where the technology to produce tritium is, in theory, available to any nation that can build a power plant. This introduces a new pathway for nuclear proliferation, one that might be harder to monitor than the fission-based enrichment facilities we track today. Finally, we're left with a more philosophical problem. Us. Not only do we need more efficient extraction technology, we need a change in mindset. What if we get it all? What if we solve the engineering, the cost, and the waste problems? What if we finally achieve limitless clean energy? Would we just use it to burn through our existing natural resources even faster? Would it really mean a lower cost of energy for everyone? What if fusion doesn't solve our resource problems, but just gives us a more efficient engine to create new ones? Does this technology save the world? Or does it just accelerate our ambition, our consumption, and our destruction of it? So, after all this, let's go back to the real timeline for controlled fusion energy. The claims of fusion on the grid by 2030 are almost certainly hype. They're bold declarations designed to attract the next round of multi-billion-dollar investments. These timelines are optimistic, but unlikely. We're still solving fundamental materials and fuel cycle problems that have no precedent. A more realistic timeline can be found by looking at ITER's progress and plans. ITER is aiming for its first full-power DT run in 2039. But ITER is not a power plant. It will not be connected to the grid. It's a scientific precursor to the first demonstration power plant, which is, in most roadmaps, not scheduled to come online until the 2050s. The private companies are betting that they can do it faster. They're betting that new materials, AI-driven modeling, and a tolerance for high-risk, high-speed iteration can reduce that timeline. Even so, the most optimistic, credible timelines for a commercial prototype are realistically still 15 to 20 years away, at best. So, has anything changed? Will fusion still always be 20 years away? I don't think so. For 70 years, research was defined by the question, will fusion ever work? That question has been answered. The NIF ignition breakthrough, along with other breakthroughs around the world, and the investments in private research have changed the story dramatically. H.G. Wells wrote of a humanity that would step from the pinnacle of this civilization to the beginning of the next. We are, perhaps, closer than ever to finally building the engine to that new civilization. The final question that I end with then is not, can we build a star on Earth? It's, what will happen when we do? If you like this investigation into the engineering and questions driving the quest for nuclear fusion, you might also like my recent video on Google DeepMind's work to finally solve a $1 million equation that has challenged mathematicians for centuries.